Welcome everyone to day 5 of the Nextflow workshop. Apologies, I still don't have internet, but I've come around to Paolo's house. He's kindly lent me his spare bedroom and his Wi-Fi, so we can get this workshop done. Thanks for making it through to the last day. I know it's sometimes a lot of material to cover, but I hope it's all been useful so far. We had a couple of questions overnight about the material, and we will be providing all this material, so all of the data, the scripts, and the HTML, so the documentation, we'll be providing to you before the end of the course. So before we shut down the VMs, we'll keep the virtual machines open over the weekend. On that note, if you're watching on YouTube or if you're watching this at a later date, we're going to be open sourcing all this material, so all this documentation in the coming weeks. So you'll be able to find that. And I mean, if there's any errors, if there's things that you would like to change, then feel free to put in a pull request for that, for example, and we can do that then. Okay. But starting with today, we're going to, we looked yesterday at the configuration of our pipelines. So we looked at how we can use the Nextflow configuration to determine various aspects of the deployment. We looked at profiles at the end there. So remember that profiles are ways of essentially defining a chunk of config, which can then be changed at the command line or using Tower for changing our profiles. And we also looked at how we can use different grid scheduling systems. Well, I want to take a moment now to start to begin this day by looking at cloud deployment. And cloud deployment is really one of the fundamental aspects of Nextflow, and I think it's one of the main reasons as to sort of explains the popularity of Nextflow is really around making this this journey that we're all on to a certain extent of migrating our workloads to the cloud, or at least using the cloud more and more in our work, and really simplifying that process for people. So when we came about starting Nextflow back in 2014, there wasn't that many services around. So there was, you can imagine the basic things of having a virtual machine, having, of course, in AWS, there was S3 buckets. And in terms of what you wanted to run with a typical analysis, you might be able to boot up a virtual machine yourself. So you can spin up an instance of it. You can choose your operating system, but then it would essentially just be like having a box in your office. And how you could connect multiple of these together, let alone do some distributed compute, was a challenge. So that's essentially what we're trying to do with Nextflow, is allow the user to run their compute, but kind of be run in a way which is transparent. So it's still running in your environment. It's still your virtual machines which are coming up. It's still with your storage. However, it's happening in a way where this is managed for you, so that you don't have to take care of all the aspects. So we're going to focus here on AWS Batch. However, there's a similar concept for Google Life Sciences. We'll just keep it. You can imagine some of the concepts are the same. So first of all, I'm just going to quickly change to go back to one of the slides that I showed you in the original presentation, just so we can see the various aspects of what happens here. So when we are now running with AWS Batch, we're going to be submitting our jobs. So we're going to say Nextflow run with AWS Batch, for example, in a profile. And each of those tasks is going to be submitting to Batch via the Batch API. And it's going to contain several things. We're going to be telling Batch, this is the container that we want to run. We're going to be telling Batch, this is the command that we want to run. Nextflow is going to run it. And we're also going to be saying, we're going to be defining which are the inputs of that task and which are the outputs of that task. This is a kind of it's very much similar way to how you would run in a distributed system, where you would be submitting your job to a scheduler, and that scheduler would place that job onto a virtual machine within your cluster. Now, in the case though, this is no longer a scheduler that's going onto a cluster. This is now a scheduler which is going to be spinning up cloud resources for you. So AWS Batch is a service for spinning up these resources, for managing the deployment of them, and for each of these tasks that will be submitted as what's called an AWS Batch job, which is submitted to an AWS Batch queue, which is in turn linked to a compute environment. We'll go over this in more detail by looking at inside the AWS configuration. But the key thing to note is that each task is submitted to Batch. That spins up the resources that are required for us. It takes the data that's required as a S3 bucket, pulls it onto the virtual machine, which is used there. The task is run, and then the output data is sent back to the S3 bucket. And this is the typical way that this is run. Okay, sorry, let's get back to the documentation now. So how can we do this? How can we do this with Nextflow? Okay. So in the same way that we had some settings before that we defined that we needed to have for running Slurm, we also have some settings that we can have with AWS Batch. So of course, there's documentation for all of this. Here is a kind of minimal set of config that we need in a Nextflow configuration file to run with Batch. You can see the first one is the executor we're specifying, in this case, AWS Batch. We specify a queue, and a queue has the same concept as a queue in a traditional batch scheduler. We'll see how this works in the back end in a moment. We have a container. Again, this could be set for all the processes in this case, or for a specific process, as we saw yesterday. And then you have a work directory. The work directory is important because this is now a location in the cloud that Nextflow is going to be using for storing the data that we saw in our work directory before. So this will be, for example, the input data, the data that's been used to actually run, and that work directory will be containing that information, and then that will be able to be transferred from there to each of the virtual machines that are running the actual tasks themselves. We also have a region here, and then this is just a specific location of the AWS command line tool, which is used inside AWS Batch to copy these files over for us. So this is something that you could put inside your config. There's an example we can look at from yesterday. If we look in this RNA-seq pipeline that we had, we look in the Nextflow config, you can see that you see something similar with the batch setup that we have here. So here we're actually defining some params inside our batch. And the reason for this is that if our data is already in S3, our input data here, then that can speed things up a lot. You can see we define a container, an executor, batch, of course, queue, and the rest is the same as we saw before. So remember, that could be called now from the command line with run, and then using the batch profile. One thing to note on that is that Nextflow is also able to stage the files to S3 from our local machine. So that means that if I was to launch locally from my laptop, say, and I was to say Nextflow run, it was onto batch, and that some of these tasks then were run on batch, the input data, if it was located on my local machine, would be staged to the S3 bucket where it was required. And likewise, for a task that was run on my local machine first, and then say a downstream task which had to be then run in the cloud, that data would then be transferred to S3. The work would occur on the VM, would go back to S3. And then if there was a downstream task that was run locally, this is when we're talking about hybrid deployments now, that would then be pulled to my local work directory and run there. We'll see examples of that later. Okay. There's various options that are you're able to use with batch. So for example, be able to mount the volumes here. This is a way that you can mount the volume inside the container job. So you have to imagine that every one of these tasks is a container job. I'm running in batch. There's some custom job definitions. I wouldn't get too much into the details here. There's documentation if you want to see exactly what's happening there. Early on, we had to, it was requirements, so that Nextflow needed a custom image. So this is a custom AMI. So AMI is you can think of it as like a VM that you use on AWS. And for each of these AMIs had to be created a custom one to run Nextflow. And the reason for that is you needed to have this AWS command line tool inside the VM that was essentially running here, that was running the jobs itself. And now there is some ways that we can actually take care of that for you now, particularly with Tower. The more interesting thing is to see, I think, is to see how this works and to see the different components of it. And we could imagine that if we were going to launch, we could do as we did before, as I showed you yesterday with Slurm, that we could just use a profile. I think that by far the easiest thing to do now, though, is now that we have Tower to create all the resources for us, we can create these resources and see where they fit in, and then watch a job actually go through in the cloud on our infrastructure. And that will help understand a little bit of the parts that are going in here. So I'm just going to log into Tower here as before, and let's run our same pipeline that we had. So I'm going to launch the same pipeline. I'm going to do this on AWS Batch EU West 1. So it's just an environment I've set up. And when I click here, I'm just going to keep everything the same. So actually, let's do a larger pipeline so we can might make a bit more sense to see something bigger run through here. Let's do an NF core one. And for NF core, we have to have a test profile. Okay, looks good. So now I'm launching the job, and I'm going to go look into AWS and see what's happening in the background. So the first case, and when you launch with Tower, is the actual Nextflow job itself is submitted to batch, but that's not a detail that we're too worried about here. We have several parts to the Aws Management Console that we're interested in. So we have the work directory, as I showed you before. This is an S3. So S3 is the storage in the cloud. If I was to go into here, I would be able to find the bucket that we're using. We see we're using this one here. This is in Ireland, and you have obviously some settings associated with it. It's not super interesting, but this is the kind of location there here. And you can see that inside here, I have all of like a typical work directory for running this. This is exactly what we had in our local machine. Something that's good to set up here would be typically like a policy that would remove this every 30 days. For example, if it's your work directory and you didn't really need to use that often. So S3 is our storage. It's going to be where our work directory is. The data is going to go in and out of that. The other interesting thing, and the service that we're using here most is batch. So this is a view of batch itself. You have several different parts to it. So you have jobs, which we're not really worried about. Nextflow takes care of that. The jobs are the actual tasks that are submitted. Again, with job definitions, this is not so important. Nextflow is taking care of this for us. This is just a definition of how the job works. What we care about is the queue, because the queue is exactly like what we have for when we're running this in the cluster. And the queue, for example, that we were using this example is this Nextflow CI. And this is just a queue that we've created for doing this. A queue has a compute or several compute environments associated with it. So the queue is kind of like the link in to the batch service. And from the queue, you have these several compute environments, and the compute environments are what are linked to a specific amount of resources or quantity of resources. For example, let's look at this one that we're using, this Nextflow CI queue that we've created. You can see that it has on-demand resources. So this means that the virtual machines that will run are on demand as opposed to being on spot. We can see that it has a minimum amount of CPUs, 16. This means 16 CPUs are always on in this queue, and it can go up to a maximum of 256. And these are the kind of core properties you're probably concerned about. Setting some kind of minimum amount, some kind of maximum amount, and then the provisioning model. Another thing you may focus on is whether you want these instances to be a specific type, so a specific machine. We typically go with optimal just because it allows us to have a heterogeneous workload where the tasks that are submitted, if they have, a batch will essentially spin up the right virtual machine for you based on the resources that you had. So we can see that here we have our pipeline is now 11 of these tasks are submitted, 1 has succeeded. So if we go now to batch, we would actually see this in our dashboard. If we were to look here along, we can just wait for this to load up. It just takes a second. We've got quite a few environments. You can see that we're using this queue here because it's a forged queue. So this is one we create on the fly. You can see that we have these 11 jobs here, and 5 of these are now succeeded. So we could follow through. So Tower in a way is a kind of an easy way to review that information. What's more interesting though is what's actually happening in the background. So we've got 5 jobs running there, but what does that mean? What's actually happening? And in the background, what AWS Batch is doing is it's a managed service for our compute. The main compute in Amazon is EC2. So if we look at EC2 here, you can see that we've been spinning up on the fly for us some instances. So these instances were spun up for our compute for us. The cool thing is that if we were doing this for spot instances, it's going to handle the spot requests for us. You can see that 3 minutes ago, it made a spot request for these type of, this is M4 4x large, and it's going to be fulfilled. That means that the virtual machines in our instances themselves will be spun up. And then as soon as these tasks are finished, with Tower and the pipeline is done, there'll be nothing else in the queue, and those virtual machines will go down. From our perspective, we don't, when you run your pipeline, you don't need to worry about these details, but it's useful to understand what's happening in the background and to help you debug a bit. Okay. Just check I've got my chat on my laptop, so I can't see anyone. I hope someone's listening. We do have participants. I'll take the word for it. Okay. How do you get started with this though? So we've been doing awesome. Thanks, Giselle. So we've been doing this for a while, and it was still quite tedious to get this set up. So to be able to create these queues, go back to batch to create these queues and to have this kind of launched for you. So what we've done recently, and this is just something from the last couple of weeks, is and it had the ability to create all of the resources on the fly. So what I mean by the resources, the compute environment, the batch queues that are required for us to do, as well as the permissions associated with that and linked to an S3 bucket. So I'll just give you a 2-minute look at how you can do this now. So if you go to compute environments, you can create a new environment. I'm going to say my new batch environment here, select the platform, Amazon Batch, have some credentials. You can find documentation on this link here on the credentials which are required to be able to do this. So you can create a role if you need. This is kind of more to understand exactly what permissions are required. For most use cases, you should be fine. Select the region. I can just select US1, select the pipeline work directory. Again, I'll just choose the same one. And then you want to use batch forge here. And this is a way of creating this on the fly. It means that the resources will be created for you. If you already have them done, you can use manual, but probably in which case you specify the queues themselves. For us, we're going to let Nextflow Tower take care of this. You can choose the provisioning model. If I want to be on spot or on demand, say, I know I want 512 CPUs if I want. You can choose EBS auto scaling. This is a way of expanding the disk of each of the VMs, so that if you never have to run out of space on that specific VM as it goes through. And then we can choose Lustre. And Lustre, FSX for Lustre, is a way of having a shared file system inside the virtual machine. So each virtual machine is linked to the central file system, and this means that we no longer need to use S3 to run this. But anyway, if I was to create this, this would then create the resources for me. And once I have this, my new batch configuration, I can simply launch a pipeline and would be able to choose it from here. It takes about 30 seconds to set up. Okay, so you can see that our pipeline here, 44 of these tasks have succeeded. You can see that we've spent 0.2 cents on running this RNA-seq pipeline. There will obviously be some other costs associated with the storage, etc. But it kind of gives you the idea that running in the cloud in this way, particularly with spot instances, and especially with the optimization that we have in the pipeline that's coming now, I mean, it's really competitive to having your own clustering resources, your own on-prem. Okay. Another really nice thing about doing it in this way is because each task itself can be defined in a way. You remember that we could say, with this process, use this container, or with this process, use this many CPUs. Well, because the executor itself is also a process directive, so the executor here is Slurm. This is saying that, in this case, all of the processes use Slurm, but I can define some. For example, I could define, if I have a big a process, which I'm going to give a label big task, then from there, all of the tasks themselves will use batch. And we sort of hinted at this before, but this means that the output of a task which was running on Slurm, on my shared file system, the input, any tasks, any data which is required as an input to a task via the channel would be taken up and placed into my S3 bucket required for batch. And this is extremely useful for what's called cloud bursting. And then from the cloud bursting, this means that I could have a situation where for the resources that I have on my local on-prem, I run on that. And then when I need specific resources, like, I don't know, imagine a high memory machine that you don't have, but you only need to use it for half an hour. No. Then you could burst that particular task into the cloud. There's a question about what exactly do the costs entail? Is this only the spot prices for those instances? Yeah, it's a good question. So when we look at the costs here, for example, this one here, we can see that it's a summation of all of the individual tasks. So you can see that this one costs this much here, and the calculation is with batch is a little bit complicated. The reason for this is that in batch you can have multiple tasks on a single VM, but you only pay for the VM cost. So we will be paying for an R4 4x large for however long that machine stays up, but that machine could have multiple tasks on it. So what we do is we split up this R4 4x large, and we split it based on either the limiting factor here. That could either be CPUs. If this has got 4 CPUs and we request 4 CPUs, then we're using the whole thing. If we're using 2 and this has got 4, obviously we're using 50%. But then you have to consider the memory as well, because if we request tons of memory but 1 CPU, we're essentially using all of the instance up. So it's a kind of limiting factor calculation based on the limiting factor multiplied by the time that you use it, multiplied by the cost of that instance in that region, and depending on the costing model, either on demand or spot. The question of when you're running, does it include the data transfer costs? At the moment, we don't have any calculations on the data transfer costs in here. This is just pure compute. Data transfer costs are real, so be aware of what you're doing in the sense that if you had terabytes of data running locally and then you wanted to do like one task in the cloud, it's probably not going to be worth your while just to transfer terabytes of data to run a little bit of compute. The transfer costs will probably outweigh what you want to do. The kind of view that we have on this, though, is that our idea is that in a very short amount of time, maybe 1, 2, 3 years, there will be a transition where all data will just become in the cloud generally, and that the idea of having on-prem data will become less and less attractive, and that there will just be a transition point when, and you can already start to see this with, like, for example, SRA, moving all of their resources onto different clouds, and we think the same thing will happen with many different data sources, and it will just become the way to run it. There's another question about when the instance cannot be fully filled with the tasks, the cost of the unused capacity is then not captured by Tower. Does that happen often, or are the instance types somehow choosing to avoid that way? It's a good point, actually. It's true that it's not captured by Tower. The view is that typically we're not running in a situation, even when you have 5 or 10 or 20 tasks, the typical pipeline will be tens or hundreds of tasks. The production pipelines that we see, like, running a full plate of Illumina will be, up to tens of thousands of tasks, in which case the granularity there is probably just going to be a rounding error versus that. But something to keep in mind if you have very few tasks. That's something we don't have much control over, in the sense that because at the moment, the way that Batch itself is submitting these tasks to EC2, so we are just submitting the Nextflow task to Batch, and then from Batch it's submitting, it's pulling up the resources for you based on the compute profile which we define. Okay. It's something that we would be interested in, though, in terms of how can we optimize it on our side, on the Nextflow side. Can we be smarter with this? And I think a lot of the optimizations that will come in here will be based around the data. So being able to, for example, tag a task. If I know that task B is coming after task A, can I just do the compute on that same VM? At the moment, it's kind of agnostic to that. It just runs everywhere. Okay. Execution, caching, and resume. So I said we mentioned this at the very, very first time we saw how we could use Nextflow resume. But I think now is the right time to have a look and exactly see the details of this. Okay. I'm just going to run out, actually. Just give me 2 moments. I get the, let's see the charger. Oh, can I get a charger? All right. Apologies for that. Okay. So we said at the very start we would look at how we can go back and how resume works in this case. And now we're going to see all the details which go into it and all the details which go into being able to resume our pipelines. So the key part of this and the way it works is that each task lives in its own working directory. But this working directory is essentially a hash. So we start with work, we have this 2 digits, and then we have the rest of the hash. This hash, the reason for doing it, splitting it into 2, as I said, is to be able to handle for some file systems that they can manage many, many tasks. So if you have tens of thousands of tasks and you had them all on a single level of the working directory, this would crash file systems and it would not work so well. So this is an example that we've run before. This is actually the same pipeline we had. Remember, we had our index, we had our, we were doing this is the results of the quantification with Salmon. And we get this number which comes about. So how does it work? So we know how to use it. We can say -resume after the run. So after this definition of the script that we wish to run. And the first thing that it does is it goes through and it will essentially, when we're running resume, the whole pipeline is executed from the start. It doesn't mean that the tasks are executed. It means that every time we run, even with resume, we're still checking everything. And the way it works is we launch from the top. It gets to the first task. So it kind of creates the DAG as it goes, as it goes through. And for each task, it's going to check, okay, does this exist? So it's going to know, it's going to calculate the hash, and it's going to say, firstly, does this exist? Okay, yes, this work directory exists, so I've seen this before. If it does exist, I'm going to check, okay, is there a valid exit code? So essentially, did the task complete? And then, yes, if the task did complete, does it have the correct output data? So not only did it complete successfully the task, I mean, like the actual execution of our task, but is the exit data there? And it's going through that step, those three conditions, so checking, okay, does it exist? Has it exited successfully, and do the output files exist for every one of our tasks, independent if it's been run before or not? We're going to run through that, and if the case is that it's all run and it all works, then we're fine, and then it's going to run through like that. Okay. The other thing we can see here about is how we can define where that work directory is. So you can, as I said, you can actually resume a pipeline or start a pipeline with a completely different script. If the task, in terms of the hash, has been seen before and the output is the same and the task itself is the same, we can actually resume pipelines that we maybe ourselves did not run. So we can have a shared working directory in some scratch directory, for example, and then all of our teammates can be able to use that and have a single location. It's also useful because very often these pipelines are creating a lot of temporary data. And if you don't have careful policies for how to manage this, one of the complaints that people have of Nextflow is that, why is my work directory so big? Well, the work directory is so big is that because it enables this ability to resume, but you still have to take care of maybe having some policy that over 30 days remove these, or if you don't care about being able to resume at all, then you can obviously be a bit more aggressive on your removal of that. But we don't try and take an opinion on this, because some analysis, it's very important that the work directory remains intact and that people want to be able to come back to their data after a year and add a single file and then rerun it. So Nextflow is very conservative on the treatment of those working directories. How is that hash completed? So there's a few blog posts on this more in detail, but if we consider that the input files that we have, we look at the complete file path of the input file that's used for that task, the file size, when it was last modified, so the timestamp. And therefore, you have to be careful that there are some file systems which actually create slightly different timestamps for the files. So be careful of that. There's some modes around how you can deal with that. Other things, some other useful tools that we can use inside Nextflow is the Nextflow log. And this is a great way of getting information about the run that you've launched, the status of it, and being able to extract some information associated with each run that you have. So when we launch a pipeline, every time we launch, we get this new run name. So this is a name which is just created on the fly, kind of like a mnemonic name for doing so. And you also have a revision or a session ID. So when we're resuming our pipeline, the session ID will stay the same. And as soon as I stop using, the session ID, so as soon as I don't use resume, we'll create another session ID. So that's the kind of way of knowing you're doing that. But you can go back and resume a particular run. So you can go back and say resume on a specific one of these runs that we have, and we can do that. So let's do a demo here. I just have to jump back into Cloud9. So we can just do a quick demo here to see how we can go back and run a different version of our, or resume, say, from a different session of our pipeline. just takes a moment to run up. Another thing that we can do is we can use the log to specifically look at the tasks which are defined from that run. So this is a run ID. So there's a run name. If I say Nextflow log on that, I can get all of the working directories that exist. And I can go further into that and I could get the fields that are associated with each of those tasks that are launched. So I can say Nextflow log, the run ID, and I say I want to know what was the name of the process, what was the exit code, what was the hash, which is also say the working directory, and what was the duration of that task. So it allows me to go back and understand the provenance of a particular run. So maybe you are running in an environment where you need to keep track of that information, and maybe you wanted to have some system where you pull out those work directories which led to a successful run. So this is a way of being able to capture that information and have a record. Of that. Okay, my machine's now here. Zoom in a little bit on this one here. Okay. So I'm sure we were running some stuff. Let's have a look at being able to run script 7. I might have to be careful here because I've got a lot of stuff in my Nextflow config. Let's even just try what we had. So if I was to do run like this, we have 2 processes. You can see that they've run. If I do resume, you can see that hopefully these are now cached. So you can see they were both cached. If I say Nextflow log on this, I can see the previous executions that I've run. The last one, is this in the order of this, is I have to go to the run a lot, run a lot there. Okay, so the latest one is actually at the bottom there. So we just ran one which was volume and spore here. I could go back and you can see that because I used resume, these 2 session IDs are the same here. I could go back and resume this specific one if I wish to. I'm not going to pronounce that. So I could say, and it would run from that location. And you can see that those are cached there. Nextflow log's got a bunch of very useful information for capturing that. We can use -F to print the information. Let's do Nextflow log on the one that we just launched. See that information. So let's say Nextflow log. Let's clear that. So again, we go back and see the run that we had. Let's say the previous execution that we had. And we say here, Nextflow log. We're going to place the name, and then we're going to put the fields that we have. There's a whole bunch of fields that we can get. I think there's something like 20 or so of these. We're going to get the process, the exit code, the hash, and the duration from there. Capture that. Oh, I've got that twice. Oh. Not so good on the keyboard here. Okay, we can see we can capture that information. You can also put this into a HTML report. So you can provide a template here where that information would go into some HTML if you wanted to create a provenance report. We get a lot of questions around resuming and how to troubleshoot this. So there's several things that can go wrong with your resume, and there's kind of several aspects you want to consider when you're both writing the pipeline, but also when you are trying to troubleshoot this. Very often people are asking, why is resume not working for me? Why am I rerunning? I'm using resume, but then I'm not getting anything out of it. I'm not getting that. It's starting from the beginning. So this is a kind of a checklist of the order of things to look at. You want to consider as an input file changed itself. So this hash that we're doing is computing on the complete path, the timestamp, the file size, etc. Another thing to note is you never want your process, you never want like a downstream process to affect an input. I mean, this is like a kind of, it creates a circularity, but you should be very clear about what inputs your pipeline is taking and not modifying those either inside the Nextflow script, of course, but even external of that as well. So try and keep the kind of data flow in one direction. Don't create a circularity, because this will break it as well. In some file systems, such as NFS, you can get this inconsistency in terms of the file attributes. So this means that a timestamp may be changed even if it's not modified. And for this, there's a different strategy which you can use. So this is essentially an option on top of your the caching mechanism. So inside of the caching mechanism, you can have deep, or you can also have lenient. And in this case, the keys provided on this, the files attributes do not invalidate that. Do not invalidate that system for doing the calculation. So just several ways of going through that. You can have a race condition. So if you can see the example here, but essentially it's where one channel is affecting a global variable. So you don't want to have a variable, for example, particularly inside of an operation here. So we have a channel, we are affecting this, and therefore this X will then, because this is global, have an effect on this channel. Now, when you do this, this is going to obviously break the parallel programming. To do this, you can get around this by having local variables. So here we're defining what the X is in this location, so that it's specific to be locally there and it's not changing this. Some other things in here, non-deterministic input channels. This comes about a bit when you're expecting that the order of the elements in the channel will remain the same over time. However, that's not always the case. So this means you can have a situation where you expect that sample one will always be with sample one. So imagine that I had some inputs here, that the output was always going to be in the same order. As soon as that changed, then this is no longer going to work. So we can read it from here. The inputs declared in 19 and 20, so this is these ones here, 19 and 20, can be delivered in any order because the execution order of the process foo, this is the ones of bar, and bar is not deterministic. So you're expecting, for example, that foos, the output of foo and the output of bar for any particular sample or any particular pair will be the same. So you are expecting that, if you had a human here and say you had three samples, say you had two samples, human and mouse, they were both running through that, you have to take note that if I was doing a BAM on here, it's not determined that the human will be first here and human will be first here, and therefore they'll be together here. I could end up with a situation where the first element emitted by the BAM channel could be human, and the second one, and the first element emitted by the BAM index channel could be mouse. And I would be in a situation where, because these two things are changing, then the resume would not work. The solution to that would be to join them on a key, or to join them. So it's take the output of the foo process and the output of the bar process and join them together, so that they are so that you always have the, for example, human sample, human together, and the mouse together. Okay. Little thing here on how we can read the error report. So there's kind of several aspects of when your Nextflow pipeline will crash. Hopefully not too often, but a lot. And you have to think about what's actually occurring. So in this area here, this is the one that we saw in our first example of the RNA-seq pipeline. What's happening is that inside the task, it's actually a task which is producing the error. So we're getting an exit code, which is produced from the Nextflow task. And that exit code in this case is telling us something. So we have the salmon command is not found. This is kind of pretty simple error, but there can be situations where the errors are not so simple. And you have to think that the first thing to consider is this an error which is being produced by the task, i.e. have I made a mistake in my command line? Is it something that I'm calling a file, for example, here, which has not been imported? Is it something that I'm using the wrong resources, or the task itself is using resources? These are all examples of task errors that will typically produce an exit code. It's very hard to provide generalized exit codes in this situation because the exit code is coming from either the application itself, the line application, or sometimes like the environment that you run, so the scheduler. And therefore, it's quite difficult to provide, kind of generalized advice on this. This is something that you have to become a little bit familiar with your pipeline, with the system that you run. Common things like not having enough memory, of course, for your scheduler. You become familiar with the exit codes that occur in that situation. First thing to do is read the error code. The next thing to do is, if it is the task itself, go inside this work directory. And once you go inside this working directory, we can actually play around and see what we can get working. So I'm gonna try and make a mistake here somewhere, and we can try and exit it. So I mentioned that we had this process here, and I'm going to output the foo process here into a file. I'm going to be calling foo.txt, and then I'm going to create an output here. So I'm going to try and capture that, and I'm going to say path, take the actual name of the thing. So it's going to be foo.txt, and then we'll just put this into a foo channel. Now imagine that I made an error here, that I'm looking for foo.txt, but I called it foo.txt. Let's save this and launch. Over here. And now we'll see the error that we get here. Search variable foo. Doing wrong here. This is from before. Let's get rid of these containers. Okay, so you can see that we get this error. In this case, the error is pretty clear. So we're getting this, that they tried to execute foo, that the output file was missing and was expecting foo. It's expected by the process foo. So what you could do here, I mean, in this case, it's fairly obvious because I kind of told you, but what I would do if it was a bit more mysterious would be to go inside this working directory. So I'm going to go inside here, just try and make this window a bit bigger. For some reason, it's lost it a little bit. Okay, so we're going to go inside that working directory and do some debugging now. Close this. Actually, let me run this again. I forgot to remember the work directory there. It's the quickest way. Okay, so now we're going to go inside dd78. So cd work dd78. And now we're inside. And remember that we have a series of files inside here for each task. So we have the .command.sh, the .command.run, etc., etc. So we will have the first thing that I always do to come here would be to look at the .command.sh. So if I do a cat on the .command.sh, we can see that this is what was actually run. If the problem was a task error, if the problem was like this was actually doing something wrong, like echo is wrong. Imagine that I mangled this. Let's consider that instead of using echo, I created a command which didn't exist. So then I can actually edit the command here. I can change this
to however I want, and I can just run it here. Imagine that I created echo, which was like obviously a command that does not exist. Now if I can go chmod plus x dot command dot sh. By doing this now I can run the dot command, and particularly if I'm not using a container, if it's just a basic command like this, I can now launch this and it will give me my error. I could then imagine that this was the error that I received. I would then go along, fix this, and change that. Now when I run my command, you can see that it's run and that I would have my foo.txt, which is created. But this is not our problem. In this case, our problem was that we were trying to look for something which didn't exist. So what we're able to do is the same thing. Is go inside here. We can change this, in this case, change this to foo. And then we can launch instead of running the .command.sh, we can run what Nextflow is actually running, which is the .command.run. Now what the .command.run does is it does all of the kind of the Nextflow magic, so kind of stages the files, checks, and it runs through the whole process of that task. So we go chmod plus x .command.run. Okay, now I can launch that command, so I can say .command.run. And we can see what happens there. Firstly, I have to change the permissions on it. Run. And we can say it ran successfully there. So if I was to change that again, there, let's go through. Oh. It's not playing well today. Go through, and you can see that you can in some instances it's quick to troubleshoot simply by changing these commands there and seeing if you're actually getting an error based on the task itself and seeing the Nextflow error. It's a useful trick to note that you can go into the work directory, go inside there and do that. What those files are themselves, so we see the .command.sh is the command script. This is .run is the wrapper. .out is the standard out, which comes from that task. Same with the .error, the standard error. We have a log, which is just a wrapper for the execution output. And then we have this .begin file, which is created when the job is launched. So this would, for example, not happen until, say, for example, the files were staging. You were transferring the files to the working directory, or in this case, the .begin would happen only when the job itself is actually launched. And remember that the launching could be a containerized task execution. We then have inside there, you'll have the input files, which will be symlinks, and the output files themselves. And this is just a description here of that information, how you can go through and look at the .command.sh, etc. Some other error strategies that we have. So we saw and several times we could actually change the error strategy, which is a directive. So let's go back to directives, and we have error strategy. Error strategy is incredibly powerful, and it's one of the most used features. It allows us to change the behavior based on what happens. So based on something, an event. We can do this at the process level, of course, because this is a directive, or we can do it on the whole pipeline level. We have several options for this. So we can choose that our error strategy is terminate, and this is the default behavior. This means that if any task has an error, that all of the other tasks are just killed instantly. And this is a kind of very strict measure. But for most cases, when you're, for example, debugging or you're developing your pipeline, you want this because you don't want any errors. Another error strategy is finish. And what this does is it comes somewhat of a graceful exit. So when the condition is raised there, the tasks which are already running, the tasks which are already initiated, will continue to run. They will finish those ones when they're complete. However, no new tasks will be created. And this is useful for if you're in a situation where you have long-running jobs. You don't want to kill all of those jobs just because there was an error in one. At the same time, you want to go and investigate what the issue was. Then there is ignore, which is you can imagine is just ignoring the jobs themselves. Remember that this will be kind of difficult to track. If you completely ignore, you're not going to get the downstream tasks running from that. But maybe there is some tasks in your pipeline which are not so critical, which you don't mind ignoring. And then the one that's probably used most often is retry. And retry allows us to retry that task, and we can retry it based on the condition as well. Related to retry, we have max retries, which is the number of times that we want to retry a task from that. And then we also have max errors, which is the number of errors which are allowed during a process execution. Okay. What's super nice is that because we have because these can be expressions, we can create something like a retry with a backoff. This means that I can say, for every time that I have a task attempt, so the first time I want you to try for a certain amount of time, then I want you to sleep, so take a rest, and then I want to increase that sleep time up until a maximum of 5 where I want to stop. What's even cooler, though, I think, is probably that dynamic resource allocation. So this is a way of increasing the amount of resources that we request to either the scheduler or the cloud or your local machine based on the number of times we try. So we're going to try 3 times here. On the first time, I want you to try with 2 gigs of memory and for 1 hour. On the second time, I want to update this to 4 and then 2 for 2 hours. And then finally, I want to do 6 and 3. You can get as creative as you want here. And there's some very sophisticated strategies that we've seen. These can also then be based on the error that you get. So if the error is specific to, for example, imagine that 140 was an error for memory in your system. If you knew that, then you could say, okay, if the error is 140, then I want you to increase the memory. If the error was time related, then I want to increase the time based on that. And this kind of automates the whole process for you for doing that. Okay, that reaches the end of the session on the kind of the core materials that we have. We'll take a break for 10 minutes or so, and then we'll come back, and I'm going to have Paolo join us, and we're going to just do a quick 5 minutes on DSL2 and just describing what we're doing with DSL2. And then Paolo's going to take the same pipeline that we've had before, that we've been running, this NF RNA-seq pipeline, and convert it into DSL2. Apologies for the people who have been who have been following along the hackathon. This will be very similar to what we saw the other day. Maybe it's useful to see it twice, but I think there's still quite a few people in the training session who were not part of that. So we'll just do that for half an hour, and then we will finish up with introduction of a larger practical exercise, which you can do in your own time, and then we will conclude with that. So I'll see you back at 40.
So we wanted to introduce a new way of running Nextflow now, which is kind of a modification on the original syntax that we have in Nextflow. And this has become increasingly sort of interesting. And one thing that was always asked about by users, particularly early on, was how can I modularize my code? So how can I take my code, the individual kind of big monolithic Nextflow pipeline that I have, and split it up into parts so that I can reuse it? And this was particularly challenging with Nextflow because of the way that the processes and the channels are intrinsically linked. The process is defined essentially with the channels into it, and therefore if you take a process out of it, the flow of the data is gone. So we wanted to be able to modularize the pipeline, modularize the components to reuse them, and then kind of have a way of having the common implementation patterns that you have and reuse them easily. So going back, we've seen this a lot now. Imagine we have our task example here. We know that now we wrap it in the process block. You can see that we link these processes together with the channels. And as I said before, because these things are linked, now it'd be very difficult for me to, for example, just take out that index sample process and use it somewhere else because it uses this BAM channel. And this BAM channel is kind of part of the definition of the process. So with DSL2, how we do this is we simply just get rid of the channels. So we can take our process that we have here, index process, and we just remove the fact that we need to define where the process is coming from. One thing to note is that you need to have this at the start of your Nextflow script. So this Nextflow.enable DSL2. This is just a flag so that you can use DSL2 in the code. So in this way now, the process definition is kind of one part. And you can think of this as like all of the processes, the modules in your pipeline can be defined in this way. And then if we wanted to use these processes, we can now import them. So we could save this in one file. This could be our modules file, for example, index modules file. And we could have these into a workflow definition now, another script. We could include them. So we're going to include the index process. This is this one from before, include the index process from some file, some module file. And then we can use it inside the workflow itself. So here we are defining, this is a new term which comes up. So instead of having just processes now we have workflows themselves. And these workflows are essentially the same as core Nextflow code. So we define some parameters. So you can see it's transcriptome from some parameter. We define some read channels, a read pairs channel from file pairs. And now the input to this process, remember that the index process has one channel, which is input, which is a transcriptome. Go back, we can see that, sorry, go back. We can see that the index has one channel, which is an input. So therefore, we have the single input there. We know that FastQC has one input, which is just the read pairs channel. And we know that the quantification step has two channels as input. One, which is the index, and one, which is the read pairs channel. So now we're separating out the definition of our processes from the workflow logic. And this is really powerful. I found it like when I started writing some big pipelines like this, it's incredibly powerful for my, for just the way that your brain can think about this is that I can focus now on one aspect of just getting my processes right, just nailing them down for a single thing, focusing on the task, what's the actual software doing. And then I can spend a next section where I can just map out the whole flow. I know, okay, this needs to go to there, that needs to go to there, this just takes the output of this. And it was really sped up my development of the pipeline and simplified things a lot, particularly around the management of these things. So the workflow block here, you can see, is a new addition. And there's also some different ways that we can use the workflows in terms of having sub-workflows. So what I mean, that's that workflows that can call workflows and also workflows which can have names. So take this, for example, here we have a workflow which is called RNA-seq. We have some new keywords here. So we can have a workflow which takes as input a transcriptome and it's a read pairs channel. It has a main section, so several different processes which run, and then it emits from the RNA-seq workflow the quantification channel here. There's another cool little feature which is DSL2 pipes. So this allows us to chain not only operators together now, but now we can chain whole processes together. So we could create a channel from some input data. Imagine this was some fast queues or some faster files here. So now we have a channel. We can pipe that channel, which means take that channel and use it as input to the split faster. Split faster is an operator. It's an operator which splits the faster files based on some conditions. Now we're going to have a channel which contains many faster files. Each one of those faster files will become an input to the process align.
So to the align process. So the align process will run for as many elements as emitted from the split faster operator. And then from that align process, we're going to pipe the output, which you can see here as the path result, to this view operator, which we can then use to actually just view the text of that. So this is kind of neat in the sense that we're using like how you would in Unix, so your kind of Unix piping, but imagine that each one of these, particularly for, say, for the align sample, is actually a distributed compute. So that's actually could be occurring across tens of thousands of virtual machines in the cloud or job submissions. And just this neat little pipe is allowing us to very quickly and eloquently describe what we want to do. So I'm going to pass you now over to Paolo, and Paolo is going to take that pipeline which we've developed, the RNA-seq pipeline we've been working on the last few days, and he's going to show us how we can very quickly convert that into DSL2, and then show you a few little tricks around doing this. So feel free to ask questions as well to that. I'm sure it should be useful. And then after that's finished, I'm just going to finish up with an introduction to a larger larger pipeline that you can work on in your own time over the next few days if you want to sort of practice some of these concepts, etc. So I'm going to stop sharing my screen now and pass you over to Paolo.
So, good morning. Yes, I'm going to show you how, how we can migrate, how we can modify an existing Nextflow pipeline to the new DSL2 syntax. I'm starting the usual pipeline that we have seen these days, our small reference RNA-seq pipeline, and how we can adapt, how we can smoothly move this into the new syntax. One important goal of this project was just to allow, to make it possible to modularize Nextflow pipeline. At the same time, we want to make it possible to allow people to not learn yet another syntax for Nextflow. So we want to have the smoothest transition to the new syntax with minimal change in the existing pipeline, and minimal change also in what you already know about Nextflow. So all the concepts that we have seen so far about channel, about data flow, about parameter, everything remained the same. And like Ivan was mentioning, the biggest change is that we are not defining anymore the connection between the processes using this from and into definition. Why? Because basically this component, the from, was linking a process definition to a concrete channel. So what it was happening is that we were defining the process, but at the same time also the relationship of this process with the upstream task in the downstream task as well. So to make it possible to transform the process definition in a generic task definition that we can reuse in any pipeline, we have to decouple this from the actual source of the data. Just remove the from and the into declaration. Let's do this into our new files. I want to copy this main into main 2. Cool main 2. Here it is. Yes, so I'm basically, I need to remove all the from, the into declaration. And doing that, basically now I have what? I have the same process definition, but now these are generic. And I mean that there is any more a strict relationship between them. And this become generic component that I can reuse in this script, or also I don't need this, I can remove for now. I can reuse this script or include in other pipeline definition. So how to recombine this with this new component that we have, workflow, that allows me to recombine the process definition. How I can use this now, this task, this process? I can use like custom function. So what it is very intuitive because once I have defined this process index or process quantification, what I can do now is to invoke like a custom function to which I pass in the input that I defined here using a position notation. So since index declare one input path, I'm expected to be able to invoke like a function to which I can pass a file. And the quantification process is declaring two inputs, in which the first one is a path and the second is a tuple. I can invoke the quantification like a function to which I will pass a pair and so on. Let's try in practice. Also, another important change, like as Evan was mentioning, that I don't need anymore to split the read pairs channel to use in two different places. Another big benefit of the SL2 syntax is that this is not needed anymore, even more is not possible anymore. So this becomes just a single channel. It makes the things much easier because I don't need to remember to give multiple names for the same thing to duplicate this channel. So much more reliable and intuitive the composition of the pipeline. Okay, so we have the workflow and we started like before with the index. We can say params transcriptome. And this is just the first piece of my workflow. Let's try to make it bigger. Then let's back to the terminal, Nextflow from main 2. Hola, not such variable transcriptome. Why not? Line 48. Oh yes, what is this? Why not? Okay, why this complaining? Because very important thing to enable the SL2 syntax, you have to declare this directive. Then the final version is going to be Nextflow enable DSL2 because we need to tell Nextflow runtime that we want to use the new syntax. And this will make it possible to use the same Nextflow runtime for the new syntax or for the old pipeline without impacting the existing code base. So to enable this possibility, you have to declare this. Since I'm not using the final release because it's going to be released next week, so far we have to use preview. Now let's try to run it. Okay, this is the usual stuff. I need to use Docker container. I have to enable the use of Docker enable true. Let's also resume all the time. Okay, now it's working. This is doing exactly what we were doing before. I think there is a question if I'm not wrong, but I can manage. Oh, I'm a bit confused with more chat finally. Oh, no. Okay, sorry. So to summarize what we have done so far to use the SL2 syntax. We have to enable the new syntax with this flag, and then basically you decouple the process definition from the implementation, the logic, the workflow that we do into this separate component of this workflow. And now we can continue to compose our pipeline using maybe the FastQC step that we define in this way, with an input that is a tuple in which there is composed by a pair that is the sample ID and the read pairs files. And we know that we have this into the read pairs channel, and we can use this way. So let's try to run it again. Okay. It's running as expected. And then basically I can continue to implement the pipeline as it was before in this way. Then I have the quantification step. The quantification step was declared using two input. One is the binary index generated by the index process, and then the read pairs channel. So this is interesting because it allows us to see how we can use the output of this task. Before we had to take a channel that was linked to the index process, but now we have the possibility to reference directly the output of the index task. So each task, each process that you define your flow can be referenced like an implicit variable to which there is the output, the scope to access the output that task. So since index was declaring for it an output path, I'm able to access a reference that output using index.out. And since there is just one output, I can take in this way. If that process was defining more than one, I could use the syntax, REST style syntax to access the component, the specific component that I need. But in this case, it's just enough doing index.out and then the read pairs ch. So this show how I can invoke the quantification task, which I'm taking the output, the previous process invocation, and then the same read pairs channel that is used twice, both like an input for FastQC and an input for quantification. Doing anything. What? Oh, funny. There is one into somewhere. Here it is. Okay, there was something still not clean. There was an extra into to be removed. Okay. And finally, we had the last step. That was the multi-QC. The multi-QC task was collecting the output of the two previous invocation, and we were using before in multi-QC this syntax to say I want to take the quantification output that was represented with quant.ch, that we were mixing two FastQC channel, and then we collecting both of them. Basically, I can use the same logic. This does not change, but now how we can do that? Because now we don't have any more quantification, but we know that is the output of this task. So become quant out dot mix FastQC ch now is the FastQC output, and then collect. So basically, what DSL2 allows to do is to get rid of all the extra naming that we had to use for the channel output of the task, and we can just use the task itself to reference the output on that task. This allows us to write the logic on the pipeline in a more consistent manner, also a bit more intuitive, because I see immediately that this channel is the output, the quantification step, and then I'm mixing with the output of the FastQC step, and then I'm collecting the result and passing to MultiQC. And then MultiQC was taking a second input that was a configuration file that, like before, was params.multiqc. Let's try it again. Okay, there it is. Cool. This is the new version of the pipeline. In DSL2, basically, the process definitions are exactly the same. We only changed, we had only to implement the core logic of the pipeline, the meaning that how the processes are invoked, they compose together. But still, we have a monolithic script that contains both processes and workflow implementation. And we said in the beginning that what we want to do is to modularize the meaning. We want to have a library of tasks. To do that, what you have to do is just to take all the processes and create a separate source file that we could call RNA processes. Enough. So an extra module is anything else that an extra script that contains only the task that you want to modularize. Does not change in any other way. And since here we have some parameter, what we have to do is to declare this parameter at the beginning of the script like we do in any other Nextflow pipelines, giving a default value. So this becomes a script that now I can include in this in the main pipeline definition using include. Then I have to declare what I want to include, that I know that I'm defining this task, or I can include index, FastQC, quantification step, MultiQC, from ./RNC processes. The extension is not needed. I could specify. Also, it's important to remember that I need / at the beginning to say that it is in the current directory. That's all. Let's try to run it again. Okay, that's exactly the same thing, and everything's cached, so it's running anything in reality. Some question maybe? It is possible to give explicit name for process output in the workflow block. Yes, I'm going to show soon. It is possible to access the desired output, or is it required to access the output via? It is possible to access the desired output in what meaning? If a process has multiple output, yes, you can access by name. I'm going to show this as well soon. You can use the emit keyword and give different output different name. Yes. our process output dealt with different whatever there is only if I use and expect a single output, but there are multiple. Regarding this question about how are managed single output, multiple output, this is exactly the same logic as before. So Nextflow allows you to pass indifferently one or multiple files, and you have to manage in your task. There is no checking for the arity of the input in the process. Even though this is something we have to improve. The idea is to add an option that would allow you to specify that you are expecting exactly one input file, or exactly two, or many, or something like this. So this is something that we need to improve. Let's see how to manage a bit more in detail named outputs. Also, another important thing that I would like to introduce, that you can create, also Evan was mentioning that we can create a module of tasks, but also a module as some workflow, a piece of code that you want to reuse, not just for a single task, but to keep together the composition different tasks. Let's say that we want to create a small sub-workflow that repeat always these three steps. And what we can do and declare in this module file or another one, this is not very important, but let's just use this for now for simplicity, a named workflow with this logic. And we can call RNA-seq pipe. So basically, a workflow can be named, like in this case, and when you don't give it a name, this is supposed to be the entry point to your pipeline. Nextflow will look for this workflow without a name when you launch the execution of the script. But you can even give it a name, like this case, and this will allow you to reference the execution on this workflow like a function like we are doing for the processes. So in the identical manner, the point is how we can define the input and the output of a workflow component like this. In the process, we are using input output. In the workflow, we have another definition, that is take. Then after take, there is the implementation of the body and emit for the output. And what does it take? It takes the input that you want to, the variable that you want to use into this block. That would be transcript, maybe, or whatever, how you want to call transcript. And then we can reuse the same name, read per ch. But what is the difference? What if I'm not declaring this? If I'm not declaring this, basically, this read per ch is expected to be a variable defined in the global scope of the script, but this is not what we want to do, because we want to make it possible to use this component, this workflow, this RNA-seq pipe, like a independent unit that can invoke and pass this parameter, because these are two input parameters that I'm expecting to use when I use this workflow. This is why I need to declare independently to declare like an input, so that now I'm able to use this name here in place of these three invocations. So instead of importing FastQC index, FastQC quantification, now I can import RNA-seq pipe. RNA-seq pipe take, we say the transcripts And so now I can use the parameter transcript tone and the read per ch. So, and what about the output of this pipe? The output could be the same that we were doing here. So this piece that I can declare here. So we are saying that the execution on the RNSE pipe is the invocation, the index process. First, you see the quantification, then produce and make quantification output, etc., without multi-QC parameter. And now this allows us to isolate this logic and reference RNSE out. Okay. And then we have params multi-QC here. Let's see if does it work. Cool. Fantastic. Now the difference now is not cache anymore because for Nextflow, these are different tasks because they have a different name. And the name is the name of the workflow column index, because the name of the workflow become like a scope in which the subtasks are executed. And then there is the multi-QC. But this is very nice because allow me to show how we can isolate a piece of logic with your workflow, how we can define the input and the output of this workflow. And then, like before, I can use like a custom function, passing the parameter like we are doing for the process, and can access the output of this workflow and like an input for the downstream task, multi-QC in this example. So naming, we were saying naming, how to give this piece a name. We can give a name, just assign into a variable. For example, all results, like this. Now doing that, I'm able to access the output of the of this combination, the quantification step at the first QC result, like we are doing here, or dot all results. Let's try. Here it is. I can use this trick to define as many outputs as I want. For example, I could take the quantification results and assign this way. Also the fast QC results. Fast QC out. So now this workflow is producing 3 outputs, but we have 3 different names to reference the result. And I have the ability to choose the one that I need. Fast QC results. Several workflows are possible. Obviously, yes. Let's see, maybe we can try to make to show it. Can there only be? Yes, there can be only one main workflow, that is the one without name, because you cannot do this, but you can give them 2 different names. And why this could be useful? Well, this could be useful because maybe you want to reference different input data. Or maybe there is also a different way how you compose some result. Maybe in this case, you want to use quantification results and in this case, yes, the fast QC result. This is just the first thing that I'm thinking, but could be just a trick to recompose some specific steps with some different input output, or maybe adding some extra step in the middle. So now we have in the main script 2 workflows, and how we could use this. Or you create another workflow main, which you call flow 1 or flow 2, depending what? A flag, params, choice equals 1 flow 1 or flow 2, just to show you the possibility of the syntax. And so now running this, I could say choice 1. I was to, why it's not taking it? Choice params, flow 1, flow 2. Then there is this bug because that's not show a wording property quant result. Okay. Come back here, quant results. I need to fix this bug that this fail fast does not show the output. Okay, now it's working. And now we're installing flow 1, RNA-seq pipe, index, etc. And flow 2. Flow 2, RNA-seq pipe, etc. And but you can even if the only thing that you want to do is to switch from one sub-workflow to another, you can do this without having to code this piece. And you can even do with the option entry, and then the name of the sub-workflow that you want to invoke. This way. This is doing the same thing like before. Then another thing that I could mention is that you can even have a library like this, which you have processes, you have a sub-workflow implementation, and you could even implement, how to say, the default invocation of this workflow. I want to come back. Okay. The default invocation could be RNA-seq pipe, to which I should give some data, and then, like before, the read period CH that I define in some way, maybe with a channel from 5 pairs, some test data. So to summarize, this idea is that you could have a library which you have processes and some sub-workflow implementation. You could have a default invocation for this workflow with some default data. And you can use this, or like the main script in your pipeline, RNA-seq processes. Okay, now it's not going to work because it's missing the transcriptome variable in somewhere. But you can switch to the implementation that you want with the entry, RNA-seq. Also, in this case, it's not going to work. But what is nice to mention is that when you import a library like this, in which there is the default workflow, the default workflow is ignored. So you can continue to use in this way. Let's back here, choice 1. Oh, I made too many things. results, still this typo. Okay, it's working like before. So you can use basically any Nextflow DSL2 script and incorporate into another, as long as you isolate the dependencies in this manner. And the workflow without a name is just ignored if the script is imported into another one. And I think it's enough. And to show the main feature of the DSL2 syntax, above all, this ability that we have to recombine not just processes, but also sub-workflow into sub-workflow itself. I think it's very powerful. And it's going to have a big impact in the way we write Nextflow with Nextflow. Thanks a lot. I'm giving back the screen to Alan.
Cool, thanks a lot, Paulo. Yeah, I echo Paulo's words there, that this is really just the beginning of what we can do with DSL2. And I think the great things about having an open source project like this is the ways that people end up using it are kind of things that you cannot even imagine to begin with. So very excited to see what everyone will do here. I'm just going to share my screen now and just go over very quickly a couple of things to finish off and to keep you busy if you're hungry for more exercises to go through. So the first thing I want to make note of is that inside this, inside the environment we have here, we have this DSL2 folder. So if you go DSL2, and inside here you can see some of the different aspects of DSL2. Each one of these has a description of what's happening, and you can go through and see a little bit more information onto those. So for example, how to do a process definition with DSL2, there should be this kind of description of what that is. So that's kind of useful if you want to go step by step through some of the things that we've seen there. Other thing that I want to make note of is a hands-on exercise that we have. Inside the documentation, you'll see that we have after training, if you write hands-on here, we have an RNA-seq pipeline that you can go through and develop kind of step by step if you want some more practice to developing more of a production-like pipeline. So with many steps, with many different channels, and see some of the how to do that. All of the data for that is inside this hands-on directory. So inside hands-on here, you'll see that you have data. So if I was to do a tree on this, you can see the information that we have. And this, you can think of this as like a project which we're going to build up. So inside here, you can see we have all of the reads that we need, the input data, and the rest of it is really left up to you. So we're doing, it's an RNA-seq pipeline using GATK. And the idea is that you call variants from the RNA-seq pipeline. There's a series of samples. These samples it's a cut down data set. So we've taken the reads, just the reads which map to the specific locus on chromosome 22. This is good kind of practice, allows you to run the pipeline through very quickly. We have some variants, etc. Here's a description of the pipeline. There's several different tools in here. I'm not going to go into how each of those work, but you can click on those and find through. The main part of the exercise is actually just focusing on the Nextflow aspect of it, so putting the things together. So these are the commands which would be run typically from a script before, and now we want to rewrite them into a Nextflow pipeline. So we have all of the data there. You can see that there's a bin folder with an R script for generating a plot at the end. We have some data and the Nextflow config. There is a Docker container which contains the material, the GATK and all the dependencies we need to run this. And then we have to make sure that they have the permissions on that script that you have. So the main parts to it, how we run through is we define input parameters. This is all set for you. What we have is a series of problems. And these problems are described in here. So once you go through, you need to define the channels. So you kind of go through, copy, paste in here, and then you have to fill in the blanks. So for example, here we're going to fill in the blanks with the correct function and the parameter from there. So in this case, you would just be, for example, creating a channel, a reads channel from our input parameters. And if you ever get stuck, you can see that there is solutions for each of these after the problem. So you can go through and see exactly what you were supposed to do there. They get progressively harder as you kind of run through it. So in this case here, we're defining where the channel's coming from, and we're building up these processes as we go along. So this will stay up. We'll keep the virtual machines up over the weekends if you want to run through this. We will also be sending out to you all of this, all the HTML, all of the data, the full environment that you have here, as well as you can also do an AWS pull of the environments if you wish to take the data that we have there. So that concludes it for the workshop. Thanks a lot for your attention. It's been a lot of fun putting this together. This is probably going to be maybe the last one of this format that we do. We're going to be open sourcing all of this material and obviously trying to get this into a way which can be scaled out a little bit better, so that we don't necessarily have to provide this in this way, and obviously looking for people who would be keen to take over that as well. The workshop itself was, in this case here, was sponsored by DKFZ and Heidelberg, as well as Cubic. So thanks a lot to them for helping put this together. The people over at NF Core is obviously part of a larger event, putting this all together. If you want to keep up to date with what we're doing, follow us over on Twitter. They're quite active on there. You'll see new developments, new releases, features that we talk about, etc. I really appreciate if you could go star us on GitHub. I know it's just like fake, internet points, but they sometimes matter and when things come up. So if you do like the project, feel free to star us. Keep in touch as well. We're always open if you're using Nextflow in production, if you're using it in your work. There's some Gitter channels to check out, obviously Twitter. Join NF Core if you want to contribute. Lots of really nice people, fantastic environment to work with. People are very supportive, and you obviously can get some, obviously just being able to run the pipelines from NF Core as well, contribute to them, makes a big difference to the community. Finally, if you want to run your pipelines, you can run on tower.nf. So this is all free to use at the moment. If you're interested in commercial deployments of this, please reach out to us. We'd be happy to do that and deploy that. Other than that, so keep in touch. Thanks a lot for your attention. I hope it was useful. And we'll be sending out an email with all of the material afterwards. So we'll probably get that out on the weekend. But follow along. There's still some talks on NF Core later on, and we'll keep in touch. Thanks a lot, everyone.
Thank you.